Okay, for 6.4, we are continuing to look at vectors, and we're going to look at their dot products, which is another operation you can do with them. Your definition of a dot product, so if you have vector u, where your horizontal component is u1, vertical component is u2, and vector v with v1 and v2, then u times v, or u dot v, my dot product, is going to be multiplying u1 and v1, multiplying u2 and v2, and adding those. So your dot product will actually just give you a number, a coefficient, no vector or anything like that. These are some properties of dot products that you want to make sure you get copied down. Some of them are properties you've seen a lot before: distributive times 0. One thing, if I do a vector times itself, then that answer is actually going to be, bless you, my magnitude squared. So finding the dot products. So I do 4 times 2 plus 5 times 3, so I have 8 plus 15, which would be 23. Over here, 2 times 1 is 2, negative 1 times 2 is negative 2, so 2 plus negative 2 is 0. Go ahead and do 3. You should get negative 6. If u equals negative 1, 3, v equals 2, negative 4, and w equals 1, negative 2, find each dot product. So on the first one, just like normal order operations, you need to do your parentheses first. So when I do the dot product for u and v, that's going to be negative 2 plus negative 12, and I'm multiplying that by w. So negative 2 plus negative 12 is negative 14. Just to make it a little easier, I'm going to go ahead and write w down. So now I'm just doing that number distributed to each of those. This is not a second dot product. You're just doing a scalar times a vector. And I get negative 14, 28. Over here, when I do u times 2v, that's really going to be 4, negative 8. Multiply my first ones, multiply my second ones, add them, I get negative 28. So sometimes with dot products, you should just get a number, but if then you have a dot product times another vector, you will end up with that vector as your answer. If the dot product of u with itself is 5, so u times u equals 5, what is the length of u? And if you look back at your properties, vector times itself is its magnitude squared. So that means that 5 is actually the magnitude of u squared, which would mean that the magnitude of u, or the length of u, is the square root of 5. Yesterday and the day before, when we were doing angles between vectors, so if here's one vector u and here's one vector v, if I want the angle between them, I showed you guys how to find that third side and do law of cosines. Well, I'm going to show you another way where you don't need that third side. You can use either way. This one's a little faster, but it's something new. So cosine of theta equals your dot product of u and v divided by the magnitude of u times the magnitude of v. So if I ask for the angle between these two vectors, that means cosine of theta equals my dot product. So 4 times 3 is 12 plus 3 times 5 is 15, over my magnitude of each of those multiplied. So for magnitude of u, that's going to be the square root of 4 squared plus 3 squared. Magnitude of v is going to be the square root of 3 squared plus 5 squared. So what's that? 5 and then radical 34. On top I had 27 when I added those. So cosine of theta equals that, which means theta equals cosine inverse of 27 over 5 radical 34. You don't have to worry about rationalizing it since you're still just using that number. It's not a final answer. When I do cosine inverse of that, I get 22.2 degrees. And that would be the angle between the two vectors. Again, you could still do finding the missing side and then treat like a triangle of law of cosines. This is just a little faster. Last thing is orthogonal vectors. First off, orthogonal vectors are vectors that are perpendicular, or the angle between them would be 90 degrees. One good way to check that without actually having to find that angle between them, all you really have to do is find your dot product, because the dot product of the two vectors, let's just say they're u and v, should equal 0. Because if I was trying to find my angle between, I would have that dot product on top. If that number is 0, then down here I'd be doing cosine inverse of 0, which happens at 90 degrees. So are the vectors orthogonal? Just find your dot product, which is 0, so yes, they are orthogonal.